What NASA found on Uranus, the tipped giant. In January 1986, as most of the world looked skyward toward the Challenger space shuttle preparing for launch, a lone spacecraft, launched nearly a decade earlier, was quietly approaching one of the most mysterious planets in the solar system. Its name was Voyager 2, and it had already transformed our understanding of Jupiter and Saturn. Now, it was on a path to a world no one had ever seen up close. Uranus, the seventh planet from the Sun, a distant turquoise orb circling the edge of sunlight. For centuries, Uranus had existed as little more than a faint star in the night sky. William Herschel had discovered it in 1781, the first new planet found in modern history, shattering the ancient boundary of the solar system. Yet for all its historic importance, Uranus remained a blank page. Even powerful telescopes showed little more than a pale blue disk. What lay beneath those clouds? What forces turned the planet on its side? Was it a twin to Neptune or something entirely different? On January 24, 1986, Voyager 2 answered, if only for a moment. After traveling nearly 3 billion kilometers, it swept past Uranus at a distance of about 81,500 kilometers, becoming the only spacecraft in human history to visit the planet. The encounter lasted barely 6 hours, a fleeting whisper of contact compared to the 13 years Cassini would later spend at Saturn. But in that instant, Voyager transformed Uranus from abstraction to reality. What it found was a world of paradox, beautiful, silent, and strangely subdued. Unlike the storm-scarred faces of Jupiter and Saturn, Uranus appeared featureless, a smooth sphere of icy blue-green hues tinted by methane gas in its upper atmosphere. Sunlight there is 400 times weaker than on Earth, giving the planet a muted, dreamlike glow. For scientists who had expected roaring storms and vivid cloud belts, the calm was shocking. It was as though the planet were asleep. Beneath that stillness, however, Voyager's instruments detected a complex and layered atmosphere. Composed mainly of hydrogen, helium, and methane, Uranus's upper clouds formed at temperatures near 224 degrees Celsius, making it the coldest planet in the solar system. The spacecraft's infrared spectrometer found almost no heat escaping from the interior, suggesting that Uranus radiates little to no internal energy. Every other giant planet glows faintly in the infrared, releasing heat left over from its formation. But Uranus does not. Why? Perhaps some ancient catastrophe, a massive collision, had long ago tipped the planet on its side and disrupted the circulation of heat within. Whatever the cause, the result was an eerily uniform world, frozen from the inside out. Yet even in this calm, Voyager 2 found wonders. Its cameras revealed a set of faint, narrow rings, invisible from Earth at the time. Unlike Saturn's wide, gleaming bands, Uranus's rings were dark and thin, composed of particles no larger than small boulders, made of rock coated with a film of dark material, perhaps carbon or radiation-processed ice. 11 rings in all encircled the planet, each sharply confined by shepherd moons whose gravity kept them from dispersing. It was a revelation. Uranus, too, was a ringed world, though one of shadows rather than light. Voyager also discovered 10 new moons, bringing the total to 27. Many of them were irregularly shaped, scarred by craters, canyons, and fractures. The spacecraft passed closest to Miranda, one of the strangest moons in the solar system, a world seemingly torn apart and stitched back together. Its surface is a jigsaw puzzle of cliffs, ridges, and frozen fault zones that rise up to 20 kilometers high, dwarfing any mountain on Earth. One feature, later named Verona Rupes, may be the tallest cliff in the solar system, a sheer drop where a falling object would take 10 minutes to hit the ground. Miranda looked like a world that had been broken, melted, and reassembled, a fossil of cosmic violence frozen in time. Scientists speculated that Miranda's bizarre geology was the result of tidal heating, internal stretching and flexing caused by Uranus's gravity, or even a massive impact that shattered and reformed it. Each of Uranus's moons, from Ariel and Umbriel to Titania and Oberon, told its own story of ice and rock, of ancient eruptions and long silences. Unlike the Jovian or Saturnian moons, the Uranian satellites seemed older, colder, and more battered, relics of an age when the outer solar system was still forming. Voyager 2's magnetometer then delivered one of the great surprises of planetary science. Uranus's magnetic field was tilted 60 degrees from its axis and offset far from the planet's center, a wild, asymmetric configuration unlike anything seen before. Magnetic field lines looped and twisted in irregular shapes, forming a magnetosphere that wobbled as the planet rotated on its side. Instead of being neatly aligned like Earth's or Jupiter's, Uranus's magnetic field swept through space like a spinning, tilted top, sometimes exposing its poles directly to the solar wind. Scientists had never imagined such geometry. The discovery hinted that Uranus's magnetic engine, perhaps a conductive layer of superionic water or ammonia deep within, worked in ways utterly alien to the dynamo models developed from Earth and Jupiter. The spacecraft's data also revealed that Uranus's rotation was extraordinary. Its axis of spin lies nearly parallel to its orbital plane, a 98-degree tilt that effectively turns the planet on its side. This means Uranus doesn't simply rotate, it rolls around the Sun like a marble spinning on its edge. One pole can bask in sunlight for 42 years, while the other remains in darkness before the cycle reverses. The result is one of the strangest climates in the solar system. Decades-long seasons where dawn and dusk last for years, and the poles receive more sunlight than the equator. Voyager 2's flyby occurred near southern summer, when the South Pole faced the Sun directly, leaving the Northern Hemisphere in eternal night. From its vantage point, Voyager saw only the lit hemisphere. The dark side, shrouded in shadow, would remain unseen until powerful telescopes decades later glimpsed faint cloud bands emerging with the changing seasons. But in 1986, it seemed as if Uranus were half a planet, a solitary sphere turning endlessly beneath a dim, distant sun. The spacecraft's radio instruments recorded faint bursts of static, evidence of lightning deep within the atmosphere. Its spectrometers detected traces of hydrocarbons, ethane, acetylene, and methane, hinting at photochemical processes similar to those on Titan or Neptune. Yet for all these clues, Uranus remained strangely reticent. The images returned showed only the barest suggestion of cloud features, a single bright streak, a few hazy belts, and the delicate gradient of its turquoise haze. To the scientists who had just mapped the raging storms of Jupiter and the glowing rings of Saturn, Uranus felt like a world in hiding. Still, what Voyager 2 achieved in those few hours was extraordinary. It provided the first and only close-up views of Uranus's rings, moons, atmosphere, and magnetic field. It revealed a planet shaped by catastrophe, perhaps struck long ago by an Earth-sized impactor that tipped it sideways and erased its heat. It showed that the solar system's diversity extended beyond the gas giants into the icy frontier, where planets were not merely colder versions of Jupiter, but entirely different kinds of worlds. After its flyby, Voyager 2 continued outward toward Neptune, its brief contact with Uranus fading behind it like a passing dream. From then on, Uranus slipped back into obscurity. No other spacecraft has returned. For nearly 40 years, the turquoise world has remained the forgotten giant, studied only from afar by telescopes and computer models. Its atmosphere has changed subtly. New storms, faint polar bands, but no human-made visitor has come near it again. The data Voyager sent back remain a treasure still being mined. Modern reanalysis using improved algorithms has uncovered hidden features in those images. Subtle cloud formations, possible convective cells, even faint auroras flickering near the poles. Yet the questions far outweigh the answers. How deep do Uranus's winds run? What drives its tilted magnetic field? What lies within its icy mantle? Ammonia, water, methane, or exotic ices under superionic pressure? The flyby also left an emotional mark. For the engineers and scientists who had guided Voyager since 1977, Uranus was the third act in an odyssey that had already crossed the inner solar system and the gas giants. The spacecraft was nearly 10 years old, operating far beyond its original design limits, yet it endured. Its instruments, powered by a fading nuclear generator, recorded history in the frozen dark. When Voyager 2's signal reached Earth, a whisper transmitted from 3 billion kilometers away, it carried the voice of a world no one had ever known. And that world, though quiet, spoke volumes. Uranus showed that the solar system is not symmetrical, not predictable, but full of accidents, collisions, and asymmetries. Its sideways spin is a cosmic scar, its faint rings a shadow of lost moons, its cold heart a mystery locked behind methane skies. Voyager's glimpse revealed beauty not in motion or color, but in silence, in the deep stillness of a planet that rolls through eternity. In the years since, Uranus has become a symbol of unfinished exploration, a reminder that even in our greatest era of discovery, some worlds remain waiting. The turquoise giant still circles the sun, invisible to the naked eye, tilted and serene. And though Voyager 2 long ago departed for interstellar space, its brief encounter endures as a promise unfulfilled, a single page in a story that demands to be finished. Someday, another spacecraft will follow, descending again into that cold, sideways world. But in 1986, for a few fleeting hours, humanity looked upon Uranus for the first time and saw a world of quiet wonder, turning slowly in the eternal blue of the outer dark. If the planets were musical instruments, their magnetic fields would be their harmonies, deep, resonant tones shaped by the invisible interplay of motion and molten metal. Earth hums with a steady, centered rhythm. Jupiter roars with the thunder of its liquid metallic hydrogen. Even Neptune's field, though odd, keeps time with its rotation. But Uranus sings in discord. Its magnetic field is misaligned, displaced, and chaotic, an off-center melody echoing through the cold vacuum. Of all the planets NASA has studied, none breaks the rules of magnetism quite like Uranus. When Voyager 2 passed by in 1986, its magnetometer detected a field that seemed to twist and tumble as the planet rotated, tilted about 60 degrees from the axis of spin and offset by nearly a third of the planet's radius from the core. Imagine a bar magnet not placed in the center of a sphere, but shoved off to one side and turned askew. As Uranus rolled on its side, this misaligned field caused the magnetic poles to swing wildly through space, sometimes pointing directly at the sun, sometimes away, creating a magnetosphere that flips like a compass in a storm. Every rotation, the entire magnetic bubble twisted, folding, and contorting under the pressure of the solar wind. The result was a magnetic environment unlike any other in the solar system. The magnetotail, the long wake of charged particles streaming behind Uranus, didn't simply stretch outward as it does for Earth or Jupiter. Instead, it corkscrewed through space, spiraling in a helical shape tens of millions of kilometers long. Within it, Voyager's detectors registered bursts of plasma waves and energetic particles, like distant thunder in a magnetic sea. It was as though Uranus's entire field were alive, wobbling, snapping, and reforming with every rotation. What could create such disorder? Planetary scientists quickly realized that Uranus's interior must be radically different from the gas giants. Jupiter and Saturn have thick envelopes of metallic hydrogen, an electrically conductive fluid that generates steady, symmetrical fields. But Uranus is an ice giant, composed largely of water, ammonia, and methane, compressed into exotic forms under immense pressure. Deep within, temperatures soar to thousands of degrees, transforming these compounds into a superionic fluid, a strange state of matter where hydrogen ions move through a lattice of heavier oxygen and nitrogen atoms. In such a world, electricity flows unevenly, convection becomes chaotic, and the magnetic field loses its symmetry. Computer simulations later showed that Uranus's dynamo, the region generating its field, may exist not in a central core, but in thin shell-like layers, offset from the planet's center. These irregular flows of conductive ice create a patchwork magnet, where localized currents distort the field into the tilted, lopsided form Voyager observed. In this sense, Uranus isn't breaking the rules. It's revealing new ones, expanding our understanding of how magnetism can arise in planets far colder and stranger than our own. The tilt of Uranus's rotation axis compounds the mystery. At 98 degrees, the planet essentially spins on its side, its poles facing almost directly toward and away from the Sun over the course of its 84-year orbit. This means that for decades, one hemisphere is bathed in sunlight while the other lies in darkness. The magnetic field, already skewed, now experiences sunlight from shifting directions, leading to bizarre and unpredictable space weather. As Uranus rotates every 17 hours, its field interacts with the solar wind in constantly changing ways, opening and closing magnetic field lines, trapping and releasing particles in pulses. Voyager 2 recorded sudden bursts of auroral radio emissions, signs that energy from the solar wind was being funneled into the planet's upper atmosphere. Unlike the spectacular auroras of Jupiter and Saturn, Uranus's auroras are faint, flickering ovals that move across the poles as the magnetic axis wanders. In visible light, they are nearly invisible. In ultraviolet, they glow dimly, sometimes pulsing in rhythm with the planet's rotation. Decades later, when the Hubble Space Telescope observed Uranus again, it detected brief auroral storms triggered by solar outbursts, proof that even in the far reaches of the solar system, the sun's breath still stirs the giant. These ghostly lights shimmer over an atmosphere colder than dry ice, a cosmic dance of particles and plasma playing out under the dim rays of a distant star. The strangeness doesn't stop there. Uranus's magnetosphere also protects a miniature ecosystem of moons and rings. Voyager 2 detected charged particle belts trapped within the field, similar to Earth's Van Allen belts, but far more intense. These regions bombard the inner moons with radiation, darkening their surfaces over time. The rings themselves, composed of carbon-rich material, may be slowly eroded by these particles, releasing dust that interacts with the magnetic field in complex feedback loops. Each of Uranus's 27 known moons experiences the magnetosphere differently as it sweeps across them, sometimes bathing them in radiation, sometimes shielding them entirely. It's a living, shifting domain, its boundaries reshaped daily by solar wind pressure and rotation. Uranus's magnetic oddities also pose fundamental questions about planetary evolution. Why is the field so tilted? Why is it offset? And why is the rotation axis itself so extreme? The leading theory suggests a colossal impact early in Uranus's history. Perhaps a proto-planet the size of Earth struck Uranus obliquely, knocking it sideways and stirring its interior. The collision would have disrupted any nascent metallic core, scattering conductive materials into off-center layers. Exactly the kind of asymmetry that could produce the field we see today. If true, then Uranus's magnetism is not just a curiosity, it is the lingering scar of a cosmic catastrophe 4 billion years old. In the aftermath of that impact, Uranus may have lost much of its internal heat, explaining its eerie lack of infrared emission. Unlike Neptune, which still radiates energy, Uranus seems to have gone thermally dormant, its convection slowed or stifled. This too affects its magnetism. A cooler interior convects less vigorously, producing weaker, more irregular flows. The entire planet appears to exist in a delicate equilibrium, where the geometry of its spin, field, and atmosphere interact in slow, unpredictable cycles. Despite its distance and dimness, Uranus offers insights far beyond the solar system. Astronomers now know that ice giants like Uranus and Neptune are the most common type of exoplanet in our galaxy, more abundant than gas giants or terrestrial worlds. Understanding Uranus's interior and magnetic field could therefore illuminate the behavior of hundreds of billions of distant worlds orbiting other stars. Its misaligned magnetosphere may even serve as a model for how exoplanets generate radio emissions, which could one day help detect their magnetic fields directly. In this way, Uranus, the planet that seems most peculiar, may actually be the most typical planet in the universe. But to truly understand it, we must return. Voyager 2's flyby lasted mere hours. Its instruments gathered only snapshots. No spacecraft has since entered Uranus's orbit to map its magnetic field over time. As a result, scientists cannot yet model its full dynamo, nor trace how its field interacts with its moons and rings. Each new telescope observation raises new puzzles: Hubble's ultraviolet auroras, Keck's glimpses of shifting storms, the discovery of faint new satellites. All hint that the planet we once thought quiet is more active than we realized. Modern computer simulations paint a vivid picture. As Uranus rotates, its magnetosphere opens and closes like a valve, alternately trapping and releasing solar wind particles. Each closure sparks bursts of energy that cascade through the field lines, igniting auroras and accelerating electrons. During certain seasons, when the sun shines directly on the poles, the magnetic geometry may even flip completely, inverting the configuration of the magnetotail. This could create magnetic storms unique in the solar system, vast waves of charged plasma curling around a planet that rolls rather than spins. There is a poetic irony in Uranus's magnetism. For centuries, magnetism on Earth has been a symbol of orientation, of finding one's direction. But here, in the far outer darkness, lies a planet that defies orientation itself. Its poles are not poles, its equator is not equatorial. Its seasons are measured in decades of light and shadow. The very concept of north and south loses meaning when the field dances like a spinning gyroscope. In Uranus, magnetism becomes not a compass, but a question mark, a reminder that nature's order is written in both symmetry and chaos. And yet, in that chaos lies elegance. Uranus's magnetic field, though twisted, still functions, still shields, still shapes the environment of its moons. It may be unstable by earthly standards, but it endures, a crooked guardian in a tilted world. When the next spacecraft arrives, decades from now, it will enter a magnetic labyrinth unlike any other, its instruments tracing field lines that curve and warp through the void. It will find not confusion, but a new kind of order, one born of imperfection. For in the end, Uranus reminds us that not all worlds obey the same rhythm. Some tilt, some drift, some twist their magnetism into strange harmonies. And yet all of them, from the giants to the smallest moons, follow the same cosmic score. Uranus simply plays its own verse, off-key and beautiful, echoing through the frozen halls of the solar system, a turquoise planet with a magnetic heart that never quite points home. For nearly 40 years, Uranus has lingered in the dim twilight of scientific memory, a turquoise ghost at the edge of the solar system, glimpsed once and then left behind. Voyager 2's flyby in 1986 remains the only human encounter with this tipped and silent world. Every other planet from Mercury to Neptune has had its orbiters, its rovers, its laboratories of light, but Uranus has waited, spinning sideways in solitude. Now, at last, its long exile is ending. In 2023, the U.S. National Academy's Planetary Science Decadal Survey, the strategic blueprint that sets NASA's goals for the next 20 years, placed one recommendation above all others for planetary exploration: send an orbiter and atmospheric probe to Uranus. The report's conclusion was clear and unanimous. The ice giants are the solar system's last great frontier, and Uranus is the one we must return to first. The reasons are both scientific and philosophical. Uranus is unique among planets, a world that defies every pattern. Its axis of rotation lies almost in the plane of its orbit. Its magnetic field is tilted and displaced. Its internal heat is nearly absent. Its moons and rings whisper of lost collisions and frozen oceans. It is, in essence, a planet that should not be the way it is. And because it is so unlike the others, it may hold the key to understanding them all. The proposed Uranus orbiter and probe mission, often called UOP, is envisioned as a partnership between NASA and international agencies, much like Cassini-Huygens at Saturn. The main spacecraft would orbit Uranus for at least 4 years, studying its atmosphere, rings and moons in unprecedented detail, while a smaller entry probe would descend into the planet's upper layers, measuring temperature, pressure, and composition directly. Together, they would reveal a world we have known only in silhouette, transforming faint data points into a living system. Reaching Uranus is no small feat. It lies nearly 3 billion kilometers from the Sun, twice as far as Saturn. To reach it efficiently, engineers propose launching in the early 2030s, when planetary alignments allow for a gravity assist from Jupiter. The journey would take 13 years, nearly as long as Cassini's entire orbital mission at Saturn. By the mid-2040s, if all goes as planned, humanity would arrive once again in the realm of the ice giants. The orbiter's goals would be as diverse as Uranus itself. It would map the planet's magnetic field in detail, tracing how its skewed geometry interacts with the solar wind over multiple seasons. It would measure atmospheric flows, watching for hidden storms beneath the methane haze. It would study the rings, detecting how dust, ice, and radiation interact in a tilted gravitational environment. And it would fly past the moons, the haunting worlds first glimpsed by Voyager, to search for geological activity, subsurface oceans, and perhaps even plumes like those seen on Enceladus. Particularly compelling is the possibility that Ariel or Umbriel, two mid-sized moons, may harbor internal oceans beneath their icy crusts. Voyager saw hints, fresh, bright surfaces, and unusual patterns of fractures, suggesting past activity. Modern telescopes like JWST and Hubble have detected subtle glimmers of carbon dioxide ice, hinting at chemical processes still underway. If an orbiter could fly through those regions, it might find evidence that even in the frozen outskirts of the solar system, the conditions for habitability persist. The atmospheric probe would provide answers to questions first raised in 1986. How deep do Uranus's winds extend? Why does it emit so little heat compared to Neptune? What are the true abundances of its primordial elements, helium, methane, ammonia, and water, which record the composition of the early solar nebula? Descending for only an hour before destruction, the probe would gather priceless data about how planets form, how they hold onto their atmospheres, and how they evolve in the outer dark. The scientific stakes reach far beyond our own solar system. In the past 2 decades, astronomers have discovered thousands of exoplanets, and among them, the most common type by far are sub-Neptunes, worlds between the size of Earth and Neptune, rich in volatile ices and thick atmospheres. We cannot yet study those worlds directly, but Uranus and Neptune are their closest analogues. By understanding these two giants, we gain a Rosetta Stone for interpreting countless planets around other stars. The data from a Uranus orbiter could therefore shape the science of entire galaxies, teaching us not only where we came from, but how common worlds like ours might be. The engineering of the mission will be as bold as its science. The spacecraft will require nuclear power, likely new generations of plutonium-based radioisotope thermoelectric generators, since sunlight at Uranus is only 1/400th as strong as on Earth. Communications will travel over 3 billion kilometers, with radio signals taking nearly 3 hours to cross the void one way. The orbiter will rely on autonomous systems, operating for hours without contact from Earth as it navigates the tilted magnetic field and the hazards of dust and radiation near the rings. Every instrument, from magnetometers to spectrometers to cameras, must endure decades of darkness and cold before the first observation begins. But the rewards will be immeasurable. The Uranus orbiter would watch a world of seasons that last decades, capturing changes in color, cloud patterns, and ring brightness as the poles slowly turn toward the sun. It would trace the flow of auroras that migrate across the sky as the planet rolls. It would record the first true weather maps of an ice giant, not just the static images of Voyager, but the living, breathing system in motion. And as it studies Uranus's moons, it might uncover signs that some of them, like Enceladus or Europa, still harbor energy and chemistry, faint embers of activity in a system once thought dead. NASA's timeline, though ambitious, is realistic. By the early 2030s, technology from missions like Europa Clipper and Dragonfly will be mature enough to support deep space operations at Uranus. The mission could launch on a heavy-lift rocket such as Falcon Heavy or SLS, using Jupiter's gravity for acceleration. After more than a decade of travel, arrival would come in the mid-2040s around the planet's northern summer solstice, an ideal time to study the hemisphere that was hidden from Voyager's view. The mission could last through 2050 or beyond, making it one of the longest and most profound explorations in history. For planetary scientists, the urgency is not only curiosity, but legacy. Many who worked on Voyager have waited their entire careers to complete the journey. We've been orbiting this question for 40 years, one NASA scientist remarked. Uranus is the planet that got away. Others see it as a philosophical mission, an act of closure. The solar system's story remains incomplete until we understand the world that broke the pattern. Indeed, Uranus's oddities may reveal more than we expect. Its offset magnetic field could shed light on how dynamo processes work in layered, conductive fluids, knowledge applicable even to Earth's magnetic cycles. Its lack of internal heat could redefine models of planetary energy balance, teaching us why some worlds glow from within while others fade to silence. And its moons, particularly Ariel and Miranda, could demonstrate how tidal forces sculpt icy worlds over billions of years, knowledge vital for understanding habitable moons elsewhere. But beyond all science, there is the human story, the longing to return to a place seen only once, fleetingly across the gulf of time. For the generation that grew up with Cassini's images of Saturn or Juno's portraits of Jupiter, Uranus represents something new, the chance to begin again. It will be the first outer planet flagship of a new century, the first step toward a complete understanding of the outer solar system, and perhaps the most hauntingly beautiful of all. When that spacecraft finally arrives, it will descend through the silence of interplanetary night, its cameras awakening to capture the first sunrise over a turquoise world unseen by human eyes in half a century. The planet will roll beneath it, sideways, serene, magnificent, its rings glowing faintly in the dim sunlight. For the first time, we will watch Uranus not as a distant sphere, but as a living planet, its storms, auroras, and moons unfolding in real time. And somewhere in that moment, Voyager's brief visit will find its echo. The lonely flyby of 1986 will no longer be an ending, but a beginning. Humanity will have come full circle, back to the tilted giant that once defied our expectations, now ready to teach us what we never knew to ask. In the deep, cold silence beyond Saturn, Uranus continues to turn, its poles aimed at eternity. The light that left the sun 2 hours ago now reaches its clouds, glinting softly off the methane haze. Soon, another light will follow, the electric pulse of a spacecraft breaking into orbit, the signal of human curiosity rekindled. And once again, across the endless night, we will listen for the whisper of a world waiting to be known.